Although I believe we are all born scientists as children, not all of us manage to continue our love of science as adults. One reason is that we hit the brick wall of mathematics. Whether we like it or not, if we are to pursue a career in science, eventually we have to learn the language of nature, mathematics. Without mathematics, we can only be passive observers to the dance of nature, rather than active participants. As Einstein once said, pure mathematics is, in its way, the poetry of logical ideas.
Well, we left off in the last segment talking about the radius of the proton and how the charge radius listed in textbooks and websites around the world isn't the real radius at all, but instead, the real radius is kind of fuzzy, like the atmosphere of the Earth. And this isn't just my opinion, though. It's an established fact. It's just something that's not usually talked about, because it doesn't really matter for most applications in physics. So what's referred to the charge radius of the proton is really calculated by this equation right here, where they say it's about equal to the radial constant, r sub 0, times the atomic weight of the nucleus to the 1/3 power. And you can look this up if you just go to Wikipedia and type charge radius. And this is just a fancy way of showing where the radius is about 80% of the density of the fuzziness, kind of like how the Bohr radius of the atom shows the maximum density of the electron cloud. And the radius where it's about this 86th percentile of the density is 0.877 femtometers, although some scientists say it might be a little bit smaller. But calling this the radius of the proton is just semantics. It's not the real radius. The real distance from the center of the proton to the real edge of the fuzziness is more like 1.2 Fermis, as it says here on the Wikipedia page. Or like you can see here from Georgia State University's website. I'm not making this up, but anyway, don't kick and scream when I say that the radius of the proton is 1.2 femtometers, and then you look it up on Wolfram Alpha and it says 0.87 or whatever. So we could think of this nucleus kind of like a jar full of marbles, and all the nucleons are the marbles, and they're all touching in this jar. So now that we know the real radii of the nucleons, well, the radius of the proton and the neutron is pretty close, so let's just use the radius of the proton that we just found for the radius of the nucleons. So let's plug in this 1.2 femtos for the radius of the nucleons in the equation that we formulated in the last segment. And if this number is really close to 1,094,000 meters per second, then we know that we're on the right track, and the speed of sound in the nucleus has a real meaning. So back to the equation from the end of the last segment. We have 1 over 2 pi times the square root of 29.05 Newton divided by 2 times 1.2 femtometers, which is the displacement, which, if you want to put femtometers in terms of meters, it's 1.2 times 10 to the negative 15th meters. And you divide that whole thing by 1.67 times 10 to the negative 27th kilograms, which is the mass of the nucleons, well, the average anyway, then multiply the whole shebang by the displacement again. 2 times the radius of the nucleons, 1.2 Fermis. So, let's type it up and put this equation into Google, because I traded my scientific calculator on the last day of school for 2 caramel apple pops, a Hostess cupcakes, and a Nutty Buddy. But in retrospect, yeah, it was still worth it. So here it is. I got it all typed up. We'll just make some copy pasta out of this and dump it into the Googles. Here we go. It's all or nothing, baby. It's all on the line. It's crunch time. And we get 1,028,300 and whoa. Hold up. 1,028,349.13. The heck is this crap? What the feezy? Man, that's not even really close. That's not even really close at all. That's like maybe in the ballpark. But ballpark isn't good enough. I said that this was going to be proof. Frank said that this was going to be proof. The hell's he had me doing? Hundreds of hours of editing video down the drain. All my research wasted. Plus, I feel bad for wasting your time too. 4.5 hours for nothing. All for nothing. At least I didn't take your money, or else I'll feel even worse. This speed of sound in the nucleus doesn't even really come close to matching the speed calculated by multiplying the speed of light times the fine structure constant divided by 2. Damn. I don't even know what to do about this. I guess we could try calling up Frank, though, on Skype and see what's up. I'm sure we calculated this right, though. I'm sure that our math was right. Screw it. Let's call him up and see. Frank, pick up the damn phone.
Hey Lane, great videos.
Yeah, man, my stuff is great, but your stuff is screwed up, man.
Why? What's wrong?
Dude,
You're scaring me.
I swear, man, we tried to calculate the sound of a nucleus, you know, the sound of wave propagation in the nucleus from first principles, and we put in the radii of a nucleon, you know, a proton or a neutron, you know, the average of them.
1.2?
Yeah, that's the radius of a proton, man. So we're putting these marbles together in the jar and going to calculate the sound of wave propagation throughout those marbles all jumbled together, and it's not producing your number, man.
Man,
it's way off.
That's what my whole theory is based on.
I know, dude. That's why I think you're full of crap.
I came up with the same problem. And what it is we have two nucleons. There they are. They're spaced by about a radius of 1.2 Fermis. You stick a third one in, there it is. You see you got a little airspace in between. They don't quite fit together. When they get in the nucleus, they squish together. They move apart a little bit to make some extra density, and they flow into the airspace.
I don't know, dude. How are they just going to magically float apart? That sounds like... Dude, you better send me some proof. You better send me some proof of this.
Just look up momentum spacing on the internet. You'll find hundreds of references. It's normally described as reciprocal of 1.36. That's in momentum space. That's really confusing too.
Do you have any papers to prove this? You know, extraordinary claims require extraordinary evidence.
Oh, I cut on, but you're killing me, Lane. You're killing me. I don't, but there's a lot of papers. Just do a search on the internet. You'll find it. Just look up 1.36 Fermis. And you know what? I did the same thing, and I got the wrong answer. And I said my whole model is wrong. I got scared. It was like 30% off of where it should be.
So what'd you do?
I worked for like a month to get a correction factor. Then I was talking to the alien scientist, and it just hit me. And I looked it up on the net, and there it was. And I got this 1.36.
Wait. So you solved backwards for what the spacing should be by knowing by assuming VT, and you solved backwards, right?
Yeah, and I got 1.36. I didn't know it was the wrong answer.
You didn't know what that meant?
No. It was the wrong answer, I thought. I was thinking, caramba, this is bad. Wrong answer. Model's all wrong. Makes so many other predictions, but if it makes one wrong prediction, the whole thing's in the toilet.
Then what do you do?
I just put in 1.36 FM ferrometers in the internet and searched, and there it was. That's the spacing of the nucleons.
Wait, so you're telling me like it's like a bunch of marbles together in a jar, except they're not even touching? It gives them a little room to vibrate?
Well, when they're in the jar, they got a little airspace in between. And it wouldn't be very good to have a void in the nucleus, and it's sort of like maybe putty. It flows into that space, and then there's a little less, so it pulls apart. So that's the effective spacing of the nucleons in the nucleus. And they call it the Fermi spacing because it's like a 0-point spacing when the nucleus is not excited. It's a normal everyday nucleus. It isn't undergoing transmutation. That's the spacing in between. So I got that answer, but I didn't know what it meant.
So what's causing the spacing? Is it like forces or something?
Well, the nucleus is stable when the nuclear force pulls them together, and the electrostatic force pushes them apart. At that point of balance, it's either expanding or contracting, and that's the state of stability, and that's where the nucleons are spaced inside the nucleus at 1.36 Fermis. And the electrostatic force acts between each nucleon, and the nuclear force, acts between each nucleon. The electrostatic force is sort of pushed out. So you have a constant density, constant force. We can calculate the velocity of sound.
So is the attractive nuclear force equalizing with the repulsive electrostatic force?
Yeah, that's the condition of a stable nucleus.
And it gives them a little distance apart.
Yeah, and they can vibrate. Sort of the best thing I can think is like shake Jello in a jar, and the whole thing's sort of quivering. And that's the velocity of sound.
Is that what gives them the room to spin, because the up spins are next to the down spins?
I don't know. I'm not that close. I just get the numbers and work the math.
Well, I mean, if the up spin's next to down spin and they were touching, then they would like slow down or something, probably, huh?
I don't know. If they're touching or what.
Well, dude, you better send me some links to prove this, and I'll check it out.
I'll get it right out. You're doing a great job. I don't want to hold you back.
All right, man. Well, I'll check him out when he gets here. Peace.
Good.
So I checked into this whole thing, the 1.36 femtos for the Fermi spacing of the nucleons, and guess what? Frank's not lying. The Fermi spacing, usually what's referred to as KF, truly is 1.36 femtometers. And if you want to check it out for yourself, feel free, because it's right. But in reality, this type of information is so specialized that it's hard to find it on the internet at all. Trust me, it took a lot of looking. Yep, you can find furniture porn online with ease, but in most cases, if you want to find out basic information about the most abundant materials in the universe, like protons or nucleons, you're SOL. Unless you want to cough up $29.95 to read a stupid paper full of jargon that you can't understand anyway. And unfortunately, I'm broke, so I can't afford this kind of crap, but with a lot of digging, I was able to come up with a couple peer-reviewed papers in PDF format for free that tells us that the Fermi spacing is indeed 1.36 femtos. The only problem is that some of them list the 1.36 femtos to the negative power. That number would be huge. Well, I'll show you exactly. See, they say 1.36 femtos to the negative first, okay? Let's put that into Google again. Remember, femtos are meters to the negative 15 power. There we go. 7.35 times 10 to the 14th meters. That's almost as big as the Milky Way galaxy. Okay, so we know that this to the negative first power is full of crap. The only reason why they're saying to the negative first power is because they're using what's called momentum space, as it says higher up in the paper, which is a theoretical way of changing the numbers around so that when you graph something, it shows up without infinities, because physicists don't like infinities. It ruins their graph. So basically, this momentum space turns the infinities to zero so they could graph it. But the real measure is 1.36 femtometers. Not to the negative first. Which, by the way, if you didn't catch it already, femtometers is just another way of saying Fermis. Well, Fermis is kind of like the slang way of saying femtometers, actually, but whatever, I still like to say it. So, in reality, the nucleus is not like marbles in a jar at all. It's more like that old retired soft drink with the floating balls in it called Orbits. Man, that stuff was good, though. I would probably commit murder for half a rack of Orbits, a few bottles of Josta, and a case of OK Soda. Oh, and don't forget the 2-liter of Pepsi Clear. And if you're interested in taking me up on this offer, shoot me an email. But back to the point, the nucleons aren't quite jumbled up with random spacing like in the Orbit soft drink. They're arranged more systematically like in a lattice structure. So let's plug in this number of 1.36 Fermis back into our equation. For the displacement of the nucleons, well, you have to multiply that by 2 and see if this works out. Hopefully, this will be closer to our speed that we got by multiplying the fine structure times the speed of light over 2. And let's type that in. And bam! There you go. Now that's undeniable. Now you know where it's coming from. It's twice the speed of sound in the nucleus divided by the speed of light. Next episode, we're doing all the orbital radii of the hydrogen atom without Planck's constant. Stay tuned.